Welcome to this explainer. Today, we're taking a journey to the absolute bottom of the stack to demystify one of programming's most infamous and honestly kind of intimidating concepts, recursion. Now, if you've ever looked at a recursive function, it can often feel like a magic trick, right? It's a piece of code that somehow loops endlessly without actually using a standard loop. It almost feels like it breaks the fundamental rules of logic. But I promise you, there is absolutely no magic here. It's a highly logical, strictly mechanical process, and today we're going to break down exactly how it works inside a computer's memory, step by step, so you can really master it for yourself.
Okay, so here's our roadmap for the journey. We'll define exactly what recursion is, break down its anatomy, dive into the memory stack analogy to see how the computer tracks everything, trace a real function call step by step, look at the explosive dangers of infinite loops, and finally, weigh recursion against standard iteration. Let's just dive right into it. Starting with Section 1, what is recursion? Let's kick things off with a fundamental paradox that makes this whole thing so notoriously confusing for beginners.
So how can a problem solve itself? Just think about that for a second. In standard programming, a function typically executes a set of instructions from top to bottom, and then, well, it finishes. But what if a function actually calls itself from inside its own body before it's even finished its first task? Well, that's recursion. It's simply a process where a function calls itself, either directly or indirectly. But you might be wondering, why on earth would we do this? It's basically a method to shrink a massive, complex problem into bite-sized, simpler pieces. Imagine you're trying to solve a 5,000-piece jigsaw puzzle, right? You don't do it by looking at the entire massive table all at once. You solve just one tiny, manageable corner over and over again until the whole picture miraculously comes together. You aren't doing the whole job at once. You're doing a tiny piece of it and then asking a clone of yourself to handle the rest.
Moving on to Section 2, let's look at the anatomy of recursion. Because to pull this off without completely crashing your program, you really need to understand the strict rulebook a recursive function has to follow.
It basically boils down to a two-part system. On one side, we have the base case. Think of this as your emergency brakes. It's the specific condition that tells the function, okay, stop, we're done here, which is absolutely crucial for preventing an endless loop. On the flip side, we have the recursive step. This is the engine driving the logic forward, where the function actually calls itself. But, and this is incredibly key, it has to call itself with a constantly shrinking input value. You literally have to be moving closer to that base case with every single step. Without the base case, you crash. And without the recursive step, well, you just go nowhere. All right, Section 3, the memory stack analogy. If a function is constantly calling itself, how does the computer keep track of all these overlapping tasks without getting horribly confused? The answer lies right here. The crucial mechanism behind this is the activation record. Every single time the function runs, the computer creates one of these. Think of it as a temporary snapshot or a sticky note. This record holds all the local variables, the parameters, and the exact progress specific to that one specific call. It then gets stored in a designated area of temporary memory called the stack. The computer essentially pauses its current task, takes detailed notes on exactly where it left off, and tucks those notes safely away. To really visualize this, imagine a spring-loaded stack of plates at a buffet. You can only place a new, dirty plate on the very top of the stack. And when the dishwasher comes to clean them, they have to grab that top one first before they can reach any of the older plates trapped underneath, right? You can't just yank one from the bottom. In computer science, this is exactly how last in, first out, or LIFO memory works.
Let's move to Section 4 and actually trace the call stack. We'll use a classic, simple programming example, a function designed to find the sum of the first 3 natural numbers.
Watch closely as we descend into the stack here. So the main program kicks things off by calling sum of 3. But to actually solve sum of 3, it needs to add the number 3 to the result of sum of 2. So sum of 3 pauses, drops its activation record onto the stack, and calls sum of 2. Well, now sum of 2 needs sum of 1, so it pauses and calls sum of 1. Then sum of 1 pauses and calls sum of 0. Do you see what's happening? Sum 3 is completely paralyzed until sum 2 finishes. We are just piling these unresolved math problems higher and higher in memory, and literally none of them can finish yet.
But then, boom, we hit the floor 0. This right here is our base case. Our function explicitly checks if n equals 0. And because it does, the endless digging finally stops. Instead of making yet another recursive call, sum of 0 simply says, all right, I'm done, and hands back the integer 0. The emergency brakes have officially been applied.
So now, watch the stack rapidly shrink as a cascade of returns triggers that LIFO process we talked about. Sum 0 returns 0 to its caller. Now sum 1 can finally wake up. It adds 1 plus 0, gets 1, and its plate pops off the stack. Then sum 2 wakes up, adds 2 plus 1, gets 3, and pops off. Finally, our original sum 3 takes that 3, adds its own 3, gets 6, and pops off. The activation records are being cleared out completely, one by one in exact reverse order.
And just like that, we arrive at our final answer, 6. That result is passed all the way back to the main program, successfully completing our journey down into the stack and safely back out again. The puzzle is solved.
Okay, on to section 5. What happens when our strict rules are broken? Seriously, what if we forget to tell the function to stop? I want you to picture that buffet plate analogy again, but imagine the kitchen is severely glitching out. It just never ever runs out of new plates to pile on top. The plates just keep coming and coming.
If you're missing a base case, your function will just call itself into infinity. It keeps slamming new activation records on top of the stack. But because a computer's physical RAM is finite, it's eventually going to consume all available space until the memory stack completely collapses under its own weight. This is a catastrophic software crashing event known universally as a stack overflow bug. And honestly, that is exactly why establishing your base case is always step 1 when writing any recursive function. Let's wrap things up with section 6, a quick reality check comparing recursion against standard iteration.
When we lay out the trade-offs head-to-head, a really clear picture emerges. Recursion gives you incredibly elegant, highly readable code. It's an absolute lifesaver for navigating complex branching stuff like file directories or tree data structures, where things naturally nest inside each other. However, as we just witnessed, it generates a brand new activation record for every single call. This overhead makes its memory usage pretty high and its execution slower. Iterative loops, on the other hand, like your standard for and while loops, reuse the exact same memory space over and over. That makes them far faster and more efficient, even if the code itself ends up looking a bit bulkier or harder to read.
So, I'm going to leave you with this provocative thought to challenge how you approach your next programming problem. Are you optimizing for the machine's memory, or are you optimizing for the human reading your code? There isn't a single right answer, but understanding the invisible mechanics of the stack definitely empowers you to make the right choice for your specific situation. Thank you so much for joining me for this explainer, and happy coding!
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos